everyone, thank you so much for clicking onto the video. Here are today's learning objectives. So the first is to understand that electronic configuration determines the chemical properties of an element, and then to understand periodicity in terms of a repeating pattern across different periods. We're then going to understand reasons for the trends and the following properties of the elements from periods 2 and 3 of the periodic table. So the melting and boiling temperatures of the elements based on given data in terms of structure and bonding, and also the ionization energy based on given data or recall of the plots of ionization energy versus atomic number. And then finally, we're going to be able to illustrate periodicity using data, including electronic configurations, atomic radii, melting and boiling temperatures, and first ionization energy. So now I'm going to introduce periodicity. And the formal definition we have is that it's the regular occurrence of the properties of elements when they are arranged in atomic number order, so like they are in the periodic table. And we'll come to find that when we look at the trends along a period, these trends will actually be the same going along a different period. And we're going to be looking at these periodic trends in period 2 and period 3. So firstly, we're going to look at electron configurations, which actually determine the chemical properties of different elements. And then secondly, the atomic radii, and then melting and boiling points, and then finally first ionization energies across these periods. So we're going to have a look at some periodic trends. So in the periods, so between period 2 and period 3, the electron configurations actually have the same kind of format. So for example, if we have a look at lithium, lithium has an electron configuration of 1s2, 2s1. And if we look at the element which is in the same group as lithium but a period down, so that'll be sodium. Sodium's electron configuration is 1s2, 2s2, 2p6 and 3s1. So what we mean is that the outermost electron is in an s orbital, and how we kind of see that is that we explain it by saying that this is the s block. So all elements in this block will have their outer electron in an s orbital. It might be 2s1, it might be 2s or 3s or 4s or 5s, depending on what period it's in, but they are all part of this s block where the outer electron is in a s orbital. And this is the same with hydrogen and helium. And then if we look at the transition metals in the middle, these are all part of the d block. So their outermost electrons are in the d orbital. And if we take these ones on the right, these are all part of the p block. So for example, boron is 1s2, 2s2, 2p1, and aluminium would be like that, but it would end with 3p1. So it'd be 1s2, 2s2, 2p6, 3s2, 3p1. And so we can see there's a pattern to the electron configurations depending on the period. It'll always kind of resemble what the element above is like, but just with an extra S kind of shell. Or in lithium and sodium's case, this extra 2p. Now we're going to look at the atomic radii of period 3 elements. And so firstly, to measure the atomic radius, we take half the distance between the centres of a pair of atoms. So if we have two atoms like this, then this centre is here and this centre is here. So we take half the distance between the centres of a pair of atoms. So we take this distance, and this would be the atomic radius. So the atomic radii of period 3 elements decrease along the period. And we can explain this by thinking about the electron configurations of these elements. So for example, if we take sodium, sodium is in group 1, and so the electron configuration would be 1s2, 2s2, 2p6, 3s1. And so we know that it has 3 electron shells. And then for magnesium, the electron configuration is 1s2, 2s2, 2p6, 3s2. And so we know that magnesium also has 3 shells. So they have very similar shielding. But what is different is that sodium has less protons than magnesium, and so the nuclear charge of sodium is less than magnesium. So we have that sodium has 1 less proton than magnesium, and so that means that it has a higher nuclear charge And so what that means is that the outer electron shell is more attracted to the positive nucleus, and so it pulls it in and the atomic radii decreases. So outer shell of electrons are more attracted to the positive nucleus where all the protons are. And so that's why the atomic radii decreases along the period, because of the similar shielding but higher nuclear charge as you go along. Now I'm going to look at the atomic radii of period 2 elements. So what we find is actually the trend in atomic radii in period 2 elements is actually the same as the trend seen along period 3. And this is again because of periodicity and how if we transfer what we've learned from one period, so the trend, to another period, then it'll be exactly the same. So looking at electron configurations again, for lithium, what we have is that it's in the S block, and then it also has 1 electron in its outer shell, and it's in period 2. So the electron configuration for lithium would be 1s2 and then 2s1. And then for beryllium, we have 1 extra electron, so we have 1s2 and then 2s2. And then for boron, this is the start of our P subshell. So we have 1s2, 2s2, and then 2p1. And so, like the period 3 elements, we have that the atomic radius decreases generally along the period. And this is because we've got an increase in atomic number. So you've got an increase in proton number. And very similar shielding. Because all of these elements have 2 shells. And so what happens is that, for example, the outer electron, the outer subshell, the 2p, in boron will be more attracted to the nucleus compared to the outer subshell of lithium, which is the 2s. So there's more attraction between the outer subshell and the nucleus. And so what we get is that the atomic radius generally decreases along a group. And we actually ignore the noble gas because that's just an anomaly. Now we're going to look at the trends in melting and boiling points of the period 3 elements. So this is a graph showing the boiling points and the melting points, and we're just going to quickly discuss through. So sodium, magnesium, and aluminium all have giant metallic structures, and so there are lots of strong electrostatic forces between the positive metal ions and the negative electron cloud. And these kinds of forces take a lot of energy to overcome, and so this leads to a generally very high melting and boiling point compared to the nonmetals. Now, the melting and boiling points increase from sodium to aluminium because of the increase in ion charge. So if we think about sodium, it forms Na plus ions. But if we think about magnesium, it forms Mg2 plus ions. And because Mg2 plus has a bigger ion charge, the metallic bonding is stronger than in sodium. So if we had sodium chloride and magnesium chloride, for example, the metallic bonding in magnesium chloride would be bigger than in sodium chloride. And so because the metallic bonding gets stronger, that means it takes more energy to overcome. And so the melting and boiling points of magnesium will be higher than for sodium. Silicon is a giant covalent structure, so it has lots of strong covalent bonds throughout the structure which take a lot of energy to break. And so this leads to a high melting and boiling point. Phosphorus, sulfur, and chlorine all have simple molecular structures, so there are very weak van der Waals forces between the molecules that don't take very much energy to overcome, and this leads to generally very low melting and boiling points compared to for the giant metallic structures and for the giant covalent structure of silicon. And so for these simple molecular structures, their melting and boiling points actually depend on the size of their van der Waals forces. And this depends on the number of electrons, like we've learned before, and how the molecules can pack together. And if you remember back to how these elements exist, so we have sulfur, which goes round in 8s, and then we have phosphorus, which goes round in 4s, and chlorine, which is diatomic, so goes round in 2s. And so the van der Waals forces in S8 is bigger than in P4, and the van der Waals forces in P4 are bigger than in Cl2, just because S8 has way more electrons and it's a lot bigger, and so the van der Waals forces will be there'll be a lot more of them, and so more energy is taken to overcome the van der Waals forces in the S8. And so sulfur, the melting and boiling point of sulfur will be higher than for phosphorus and chlorine. Now we're going to have a look at the trend in melting and boiling points of period 2 elements. So as you can see, it peaks towards group 4, and this is because lithium and beryllium both have metallic bonding, and so they have very high melting and boiling points. Beryllium has a higher melting and boiling point compared to lithium because it forms 2+ ions, so it has a higher charge density. So these 2+ ions are more attracted to the negative electrons in the delocalized C, and so the strength of metallic bond in the beryllium is higher than in lithium, and so more energy is needed to overcome these strong metallic bonds, and so the melting and boiling points of beryllium are higher than for lithium. Boron and carbon are both giant covalent structures, so they have lots of strong covalent bonds which take a lot of energy to overcome, and their melting and boiling points are actually higher than those for lithium and beryllium. And then nitrogen, oxygen, fluorine, and neon are all simple molecules, so they only have very weak van der Waals forces between the molecules, which don't take a lot of energy to overcome. And all of their melting points and boiling points are very, very low, and they're all actually quite close to each other. And that's because nitrogen, oxygen, and fluorine all come as diatomic molecules, so all of their sizes are very similar. The first ionization energies of period 3 elements. So the definition of first ionization energy is the energy required to remove an electron from 1 mole of gaseous atoms to form 1 mole of gaseous 1+ ions. And so we have the general trend that the first ionization energies increase along a period. And this is because of 2 reasons. The first is that nuclear charge increases. So there's a stronger attraction between the positive nucleus and the outermost electron. And the second is that the amount of shells, the number of shells in each period 3 element is the same. It's just 3 shells. And so they all have similar shielding, a difference. And so overall, the attraction to the nucleus that the outermost electrons feel increases along the period, and it takes more energy to remove it as you go along the period, and hence why the first ionization energy generally increases along the group. However, there are 2 important exceptions. So first we have aluminium, and this is because the p electron is in a higher energy level than the s electron, so it takes less energy to remove it. So if we have a look at the electron configuration of aluminium, we have 1s2, 2s2, 2p6, 3s2, and 3p1. And then the electron configuration for magnesium is 1s2, 2s2, 2p6, and 3s2. And so we see that this electron and the 3p1 is in a higher energy level compared to the electrons in the 3s's. And so it takes a lot less energy to remove that electron. And so the first ionization energy of aluminium will be lower than for magnesium. The second exception is sulfur, and this is because two of its p electrons are paired in a p orbital, so one of these will be easier to remove than an unpaired one due to the repulsion of the other electron in the same orbital. So if we have a look at the electron configurations of phosphorus and sulfur, so phosphorus we have 1s2, 2s2, 2p6, 3s2, and 3p3. And then for sulfur we have 1s2, 2s2, 2p6, 3s2, 3p4. Now initially we don't really know, we can't really see why sulfur will have a smaller ionization energy. But if we draw out the different energy levels on a diagram, it becomes a lot easier to see. So if we have the 1s and then 2s, then we have 2p and 3s and then 3p. So I'm drawing this in increasing energy. And so if I fill out for phosphorus, so we've got the 1s2, and then we have 2s2, and then we have 2p6, but remember that they always have to fill out one by one first. So we have 3, and then we have the other 3, and then we have 3s2, and then for phosphorus we have 3p3. So we have 3 electrons, and they're all separate. However, for sulfur, we have an extra electron. So we have 1 electron here. And so this means that one of these electrons in this suborbital will be easier to lose. And that's because of the repulsion between these two electrons. And so that's why the ionization energy for sulfur is smaller than for phosphorus, because in phosphorus the 3 electrons are all in separate suborbitals, so they don't feel any repulsion, so it's less easy to remove that outer electron. And this trend that we see in period 3 elements is actually the same for period 2, so it can be applied to other periods. And this is because in the periodic table the trends carry along, so the trends repeat every period. So now we're going to look at some questions. The first question says, state the type of structure shown by a crystal of silicon and explain why the melting point of silicon is very high. And so silicon has a giant covalent structure. And it's really important to remember that it's a giant structure, because you might think that because it's a non-metal, it forms a simple molecular molecule, but it actually has a giant covalent structure. So it still has the covalent bonds, but it forms a giant structure. And so it has a really, really high melting point because these strong covalent bonds take a lot of energy to overcome. So giant covalent, and there are lots of strong covalent bonds which take lots of energy to overcome. And that's why we have a very large melting point. And then for B, state the type of structure shown by crystals of sulfur and phosphorus and explain why the melting point of sulfur is higher than the melting point of phosphorus. So sulfur and phosphorus are both nonmetals, but they don't form giant structures. So they are simple molecular structures. And so that means that they have very, very low melting points compared to the giant covalent structure of silicon. And so the melting point of sulfur is higher than the melting point of phosphorus because when we draw out the molecules, the sulfur molecule is much bigger because sulfur exists in 8s and phosphorus exists in 4s. And so the molecule of sulfur is much, much bigger. And this means that it has stronger van der Waals forces between the molecules, and so they take more energy to overcome. So we have that sulfur exists as 8 atoms in a molecule, whereas phosphorus is 4. And so that means that sulfur is a bigger molecule, and so has more electrons, and therefore stronger van der Waals forces, because they both have van der Waals forces as they're both simple molecular structures, but it's just because the sulfur is much bigger, so it has stronger van der Waals forces between the molecules. And so more energy is needed and so that's why we have a larger melting point for the sulfur compared to the phosphorus. So before I start on question 2, feel free to click off the video and try it for yourself first. So the following diagram shows the first ionization energies of some period 3 elements. For A, draw a cross on the diagram to show the first ionization energy of aluminium. So if we have a look at magnesium and we have a look at its electron configuration, it'll be 1s2, 2s2, 2p6, 3s2. And then if we have a look at aluminium, we have all of that. So 2s2, 2p6, 3s2. But we have an extra electron, 3p1. And what we know is that 3p is of a higher energy level than 3s. And so this means that this electron that we're going to lose for the first ionization energy is actually going to be easier to remove because it's in a higher energy level. And so the cross should be somewhere about here because it'll be much less than magnesium and it'll also be less than silicon because silicon has an extra proton. The atomic number has increased by 1, and so the ionization energy of silicon to remove that 1 electron will be higher than for aluminium. And then for B, write an equation to show the process that occurs when the first ionization energy of aluminium is measured. So again, the definition of first ionization energy is the energy required to remove an electron from 1 mole of gaseous atoms to form 1 mole of gaseous 1+ ions. And so we have 1 mole of gaseous aluminium, and we're forming 1 mole of Al+ ions and an electron. And then for C, state which of the first, second, or third ionizations of aluminium would produce an ion with the electron configuration 1s2, 2s2, 2p6, 3s1. So aluminium we worked out was 1s2, 2s2, 2p6, 3s2, 3p1. And so now we just work out how many electrons we're removing to get to 3s1. So we're removing the 3p1, and then we're removing the 3s2, and then we get onto the 3s1. And so that means that we've lost 1 electron here and 1 electron here. And so we must have the second ionization energy, because the first ionization energy we would have lost the 3p1, and then the second ionization energy we would have lost the second electron in the 3s, so this 3s2 electron. And so then that would leave us with the 3s1. And so the answer is second ionization energy, or second ionization. And then for D, explain why the value of the first ionization energy of sulfur is less than the value of the first ionization energy of phosphorus. So if we have a look at the electron configurations, we have sulfur is 1s2, 2s2, 2p6, 3s2, 3p4, and then we have phosphorus, which is 1s2, 2s2, 2p6, 3s2, 3s3. And so it's not really that obvious, 3p3, sorry. So it's really not that obvious why sulfur will have a smaller ionization energy than phosphorus, like we can see on the graph here. And if we draw out the energy levels, it actually becomes a bit clearer. So we have a box of 1s2, then 2s2, 2p6, 3s2, and I'll also draw out 3p6. So this is increase in energy. So these are all the energy levels. So if I fill out for phosphorus, so we've got 1s2 and 2s2 and then 2p6. And remember that they always fill out individually first, so that's 2p6. Then we have 3s2, and then we have 3p3. So phosphorus has this kind of electron configuration, but sulfur has an extra electron here because it's 3p4. And so what that means is that this electron here, or one of the electrons from this suborbital, is much easier to remove. And that's because there's repulsion from the two electrons in the same suborbital. So we've got repulsion from the other electron. Compared to in phosphorus, when we just had 3 of them separately in their own suborbitals, then it's actually harder to lose one of those electrons compared to one of the ones in this suborbital box because of the repulsion between them. And so that's why the ionization energy of sulfur is smaller than that of phosphorus. And the last question says, identify the element in period 2 that has the highest first ionization energy and give its electron configuration. And so if we think about it, so we know this trend of period 3 elements, and we can just apply this for period 2 because the trends repeat every single period. And so because chlorine has the highest first ionization energy for period 3, that means that fluorine must have the highest ionization energy for group 2. Because in general, the ionization energy increases along a period because of the increasing nuclear charge. And so the outermost electron feels more attraction to the positive nucleus. And so it gets harder and harder to remove the outer electron when you go along the period. And so fluorine will have the highest ionization energy, the first ionization energy. And the electron configuration of fluorine is 1s2, 2s2, 2p5.